Hello, hello. Aha. Do we have audio? I think we should have audio. Can you guys hear us? If you can hear us, please type something into the chat. Okay, let me quickly introduce how this is going to work. And I also want to introduce my wonderful co-host as we go. But first, the way that this system works is you've probably noticed that if you're inside the Zoom room, you can talk and your comments might actually appear here. The way that works is you send a message to chat relay. Don't send a message to everyone, doesn't work. And don't send a message just to me because I'm not even in the room. But so send a message to chat relay and it's going to appear here maybe. The way the system works, by the way, is that there's lots of messages coming in all the time. And one of them is picked at random. But some messages are more lucky than others. What that means is if you write a lot of good comments, the moderators might give you some stars. Stars means that your comments were good, interesting. And then the more stars you have, the more likely it is that your comment will appear if there's several of them at the same time. But if you say something that's not super nice, we'll give you an anti-star, which is like an X or something. Don't worry, those don't show, but it'll make your question, your things less likely to appear. All right. Well, we're on number 3. We're on the third live solve for the chapter Math Counts. And I would love to introduce my amazing co-host here. Michelle, can you just make us say something and then you'll take over the screen and I'll say something about you.
Sounds good. Hello, everyone. My name is Michelle, and I'm super excited to be here with you guys today.
Yes, and I'm super excited to be here with Michelle too. Michelle is a fantastic high school student. Right, we've actually been working together on all of this math teaching for a while. She goes to Montgomery Blair High School, which is one of the extraordinary schools in the United States of America. And actually, she has math competition background as well. She actually participated in the University of Maryland math competition and was honorable mention in that. And at the same time, many of the people that we work with are not only interested in math. In fact, she also plays violin and volleyball, and she enjoys physics and coding as well. So this is my co-host right now. There might be another person coming on in at some point during this live solve, and when that happens, we'll also introduce him. But the way that the system is going to work is that we're just going to go through these questions. And if you have never seen a live solve before, what that means is that we haven't actually solved the questions before. So we're going to have to go and try to figure them out as we go, and we'll work together too. And we usually take turns. We kind of take turns going off on one question and then the other question and so on. And of course, we might have some comments on each other's work too. So I guess I'll just go ahead and get started. The reason I like to start is because then I get to do the easier questions. Okay, well, I'll do the first question first. Oh, yes, very important note. This is official collaboration with MathCounts. And so problems here are copyrighted. Please do not just copy MathCounts problems and put them everywhere. Let's respect MathCounts. Let's keep going. Oh, wow. Oh, wow. Oh, okay. One thing, if you're new to MathCounts, this is called the target round. Target round means that you can actually use a calculator. So I've brought an old school calculator. I'm kind of lazy. Sometimes I don't use the calculator, but we'll see. Alton paid $31.50 for 15 coloring books and 3 boxes of crayons. A coloring book costs half as much as a box of crayons. How much does one coloring book cost? Okay, when I see a question like this, the way I usually go is I say, what's the unknown that I'm trying to figure out? I want to know the cost of a coloring book. So I wonder if I can express the amount of stuff I have in terms of a number of coloring books. And I see that there are 15 coloring books. Okay, but then I also have 3 boxes. Oh, I shouldn't say 3 crayons. It's actually 3 boxes of crayons. Okay, but then when I see these two together, I also notice that the coloring book is half as much as the box of crayons. That means the box of crayons is actually twice a coloring book. So I could actually say this is 6 coloring books. This is how I like to shortcut my work. I'm looking at this and I'm saying, you know, it's as if I had 15 plus 6 coloring books altogether, right? Because then I can wonder, well, it's 3150. Can I do a division? So the way I think about it now is I'd say that 3150 is 21 coloring books. Okay, and then the rest of the question becomes, could I divide? Can I divide 31.5 divided by 21? I think it's just 1.5. So I have to say, I actually hate using calculators. Whenever I use them, I start typing things in and I make typos. But when I look at this, I'm like, the question can't possibly be, $1.66.666666. Math counts won't do that for you. So it should be something nice. So I'm just looking at this and I'm like, if I have 30-ish divided by 20-ish, can anyone tell me approximately what ratio that might be? If I have 30-ish divided by 20-ish, that's like 1.5. Yeah, thanks everyone. Thanks, Andrew. 3/2. We've got all these different ways of looking at it. So I looked at this and I was like, it's sort of like 3:2. Could it possibly be? Could it possibly be that each coloring book is $1.50? Well, then in my head, I took 1.5 times 21, and I got 21 times 1.5. That was 21 times 1, which is 21, plus 21 times 0.5, which was 10.5. And that was actually 31.5. And I got happy. And I said, that means the answer is probably $1.50. Is it right? Yay!
That's awesome. I especially love how even though we do have a calculator in this round, you realize that 31.5 divided by what was it again? 21 was something that you could actually do in your head, which I think is incredible. And now on to our next question. A fortnight is a period of time measuring 2 weeks. If a micro-fortnight is defined to be 1/1,000,000th of a fortnight, how many seconds long is a micro-fortnight? Express your answer as the decimal to the nearest hundredth. Okay, so I'm looking at this problem and I'm thinking we're dealing with time. And in specific, we're dealing with different units of time. So we have fortnights, we have seconds, we have this weird micro-fortnight thing that I've never heard of. So because we're dealing with time, I think just to keep us on track, let's make sure we are very careful about our units and how we're converting things. So we're trying to find what 1/1,000,000th of a fortnight is in seconds. Well, okay, so let's just start by writing that out. 1/1,000,000th of a fortnight is a fortnight divided by 1,000,000. 2, 3. And I want this in seconds. But we know that a fortnight is a period of time measuring in 2 weeks. So we can express a fortnight, I'm just going to simplify it as F, as 14 days because there are 14 days in a week. And then I know that in a day we have 24 hours. So that's 1 day and 24 hours. And then from there, I can convert my hours into minutes by doing 16 minutes in an hour. So I'm just going to go ahead and write that here. And last but not least, I can take my minutes and convert them into seconds by doing 60 seconds in a minute. And again, I could probably do some mental math here, but I'm just going to go ahead and cheat and use a calculator. And so luckily, thank you, Google, for existing. 14 times 24 times 60 times 60 divided by 1,000,000. And Google is telling me that my answer should be 1.2096 seconds. And we want to round our answer to the nearest hundredth. So that means 2 decimal places. And exactly like Andrew says, we get an answer of 1.21 seconds. Yeah. And
Yay!
Yay.
That's very good. So, okay. So I guess that finishes the first pair of questions. I should say it's not quite fair because the questions on math counts, by the way, on the target round come in pairs. So 1 and 2 are together, then 3 and 4 are together. And it's always, the pairs are always easy and hard. So right now it's not quite fair because Michelle's doing all the hard ones. But what's going to happen is, let's do the next one. Maybe I'll do the first, you do the second. But then for the next pair, if we don't have another person jumping in yet, let's actually have Michelle do the first and I do the second. That way it's sort of more even. So if we don't have someone else jump in, Michelle will do 2 in a row after this. But let me see what I can do here. Question number 3. This is the easier one of the pair. In the following sequence, each term is the sum of the 2 previous terms. A, B, C, D, 8, 15, 23, 38, 61. Ah, yes. So whenever I add 2 of the previous terms, I get the next one. This is like the Fibonacci sequence. Yes, Nathan Liu made a comment that's appearing right here. It is a Fibonacci-like sequence. Not exactly the Fibonacci sequence. Fibonacci sequence starts with 1, 1, and then does this. Oh, interesting. There's somebody else named Aston who knows that this is something called the Lucas sequence. You could think of it that way. This is a more general thing. So, okay, well, let's see. I need to know A plus C. All right. I guess I would just go backwards. I see that's what other people are saying in the chat. That is actually what I'll do. I'll just start going backwards. So if I have something plus 8 is 15, can anybody tell me what plus 8 equals 15? Yes, I see people saying that is 7. 7 plus 8 is 15. All right. Well then, what plus 7 is 8? What should go here? So what plus 7 is 8? Thank you, everybody. It's 1. Then if I keep going back, then I need B plus 1 is 7. So in that case, what plus 1 is 7? Oh, yes, that's 6. Okay, and we're almost done. We need to know A plus C. So I need to know what plus 6 is equal to 1. Oh, negative numbers. What plus 6 equals 1? Negative 5. Thank you very much. I see Oliver put that out. So negative 5. And finally, we put everything together. A plus C. Oh, the answer is negative. So A plus C is negative 5 plus 1 equals, I think it's negative 4. Is that right? Yay! Michelle, on to you.
Yes, that's a wonderful, wonderful question. And on to our next question. In trapezoid ABCD, shown here, vertex A is the center of the circle. Vertex D lies on the circle, and vertex B and C are right angles. If AB is equal to 14.9 centimeters, BC is equal to 5.3 centimeters, and DC is equal to 9.6 centimeters, what is the area of the shaded sector of the circle? Express your answer as a decimal to the nearest 10. Okay, so this is definitely a weird figure. Like, I've never seen this figure before, and maybe you guys have, but a circle with this trapezoid, not something I see very often. So instead of focusing on this figure exactly, let's just try and focus on what we're trying to find. In particular, we're trying to find the area of this shaded section. So how can we find the area of the shaded section? Well, one way we can find the area of the shaded section is to find the area of the circle and find what percent of the shaded section is the area of the circle. So that would require us to find this angle, let's just call it theta, and then find the radius of the circle. Because once we find the theta value, we can find what percent of the area is that shaded section. Okay, so let's start by finding the radius of the circle first, because I feel like that's going to be easier because we already have a bunch of side lanes, and unfortunately, we don't have many angles to work with. If we drop a perpendicular from D to AB right here, what we end up finding is that we have another right triangle. In particular, what's awesome about this right triangle is that the hypotenuse is actually the radius of our circle. And that's really good because we know how to find the side lanes of right triangles. We have this wonderful thing called the Pythagorean theorem. And so let's see if we can find the legs of this triangle. Well, this vertical leg right here is just going to be 5.3 since it's the same length as CB. And what about this horizontal leg? Well, I know that that horizontal leg plus DC is going to be AB. So this horizontal leg is going to be AX, which is going to be 14.9 minus 9.6, which gives us a 5.3. Ooh, okay. I see something very, very magical with math counts going on. Well, do you guys think it's just a coincidence that 5.3 and 5.3 happen to be the legs of our triangle? I don't think so. And yeah, Kiki and Andrew are onto something. No, this triangle is very, very special because it's an isosceles triangle. And in particular, what's even more special about this triangle is that it's a right isosceles triangle. And because it's a right isosceles triangle, we know that this angle here is going to be 90 degrees, but because we know that the other two angles are going to be equal, we know that these other two angles are also going to be 45 degrees. And yeah, hey, so back on track with what I was trying to say before about finding the radius of the circle. Now let's just call this radius r. Using the Pythagorean theorem, we know that r squared is equal to 5.3 squared plus 5.3 squared. And at this point, we can solve for r. But what are we actually trying to find? We're trying to find the area of the circle. And what is the area of the circle? Well, the area of the circle is pi r squared. So it wouldn't exactly make sense for me to find r directly because I already have it in r squared. So pi r squared is just going to give us pi times 2 of these 5.3 squares. Okay. And now back to our angle part, where we know the area of the entire circle, but we're now trying to find this little arc section. And what we know is that the entire angle of the circle is going to be a full 360 degrees. But we only want 45 degrees out of this entire 360. So our area is going to be 45 out of 360 of that circle, which is going to be 45 over 360 times pi times 2 times 5.3 squared. And again, this is some complex algebra that I am not going to do. So luckily, Google comes in clutch again, and we're just going to plug this into my browser. Okay, 45 divided by 360 times pi times 2 times 5.3 squared, which gives me 22.06. And it asks us to round it to the nearest tenth, so 22.1. Yay.
Yay.
And hopefully, yes.
Yay, that was good. I have to say, as you were doing it, I was also puzzling through it, and I was very happy when you found out when we both found out it was a 45, 45, 90, because I was like, how do middle school students know trigonometry? This is not going to work. Okay, great. Actually, at this point, it turns out that we have another special guest here. We now have another co-host who I'd like to introduce to everybody. And so there will be three of us bouncing around these questions. Jesse, can you make some sound and I can then intro you? In order to make some sound, we need to unmute.
Yes, that is very important.
Wonderful. And this is Jesse. Let me tell you a little bit about Jesse, everybody. Jesse is amazing. I've had the chance to work with him for quite a while as well. So he's the leader of a statewide math competition program. And he has also placed top 6 in national math competitions before. He also does computer programming. He has a perfect score on he had a perfect score on the USA Computing Olympiad bronze division. But I also have to say one of the most fascinating things about Jesse is that he always has very interesting t-shirts. Yes. So, okay. Yes, we'll understand more about the shirts later as we go. But in any case, now that we have three of us, let's just have this round robin as we go. So, Jesse, why don't you take the next one?
Awesome. Hi, everyone. So now we're on to question 5. And this one says, 4 friends, Wally, Eli, Yuko, and Sam, live in different neighborhoods, and they commute to school every day by bus. Eli's neighborhood is half as far from school as Wally's. Yuko travels as far as the total distance traveled by Wally and Eli, and Sam travels 3 times the distance that Wally travels. Okay, that's a lot of things to think about, and the ultimate problem we want to find is how many blocks Wally travels to school if all together they're going to travel 888 blocks. And I really like the suggestion by Andrew that says to assign variables. Now, luckily, the names that they gave us are all starting with different names, so we'll use W for Wally's distance, E for Eli's distance, Y for Yuko's distance, and S for Sam's distance. And now if we go back to our problem, we can set up a bunch of relationships between these variables. So first off, we have Eli's neighborhood is half as far from school as Wally's. So this means that the distance that Eli is going to travel is going to be 1/2 the distance Wally travels. So W is equal to 2 times E. Then we have Yuko travels as far as the total distance traveled by Wally and Eli. So Yuko is going to be equal to W plus E, which because W is equal to 2E, then 2E plus E, that's going to be equal to 3E. And last up, we have Sam travels 3 times the distance that Wally travels. So S is equal to 3E, is equal to 3W, and that's the same thing as 6E. Okay, now luckily for us, all of these are in terms of E. So we can figure out the total distance that all the friends are going to travel is 888. So W plus E plus Y plus S is equal to 888. But now let's substitute all of our values of E back in here. So W is 2E, E is just E, Y is 3E, and S is 6E. So if we add all of this up, then we're going to get 12E. And 12E is equal to 888. Now, luckily for us, we do get calculators. So if we divide this out, we're going to get E is equal to 74. But we're not solving for E now, are we? Because we need to figure out the distance that Wally is traveling. So we said earlier that Wally is equal to 2 times E. So 2 times 74, that's going to give us 148. So the distance traveled by Wally to get to school is going to be 148 blocks. Of course, we got to check our answer though, right? Let's see. 148, we did it.
Yes, wonderful. Okay, so I think in that case, then I'll take the next question. So this is good because now we have an odd number of people. So we're not always going to put a person on the hard question as we go. So I guess I'll take the next one. Oh boy, that is a very interesting phrase. Suppose that 4 letters are chosen at random without replacement from the phrase Mazamora Morada. Where's that phrase from? Is that a reference to something? I don't know. Maybe someone can tell me. Fun problems. Okay, I guess we're just having fun. What is the probability that the 4 letters chosen can be arranged to spell amor? Express your answer as a common fraction. Okay. By the way, I should say, if you have just joined the Zoom meeting and you're wondering how people are typing like this, the secret is you send messages to Chat Relay. There's a user called Chat Relay. Just send messages there and your things will appear. All right, so I'm basically asking for the probability that you get an A, an M, an O, and an R. Oh, there's a Z there too. Interesting. Okay, so I need to know the probability that I get those 4 letters. Oh, and somebody has told us that this Mazamora Morada is a food. Oh, it's a type of pudding. Oh, that's cute. We learned stuff. That's interesting. Okay, yes, we need to find how many of each letter. So, okay, what kind of letters do I have? Let me put the letters in alphabetical order. So let me do it over here. How many A's? How many M's? How many O's? How many R's? How many? Oh, there's D's here too. Wow. So I want to just keep track of what we might have here. There's A's, D's, M's, O's, R's, and Z's. Are there any other letters, anyone? R, D, Z. I think we got all of them. Okay, great. Now let's just count how many of each one we have. So, okay, how many A's? This is actually hard. I have to count. All right. How many A's? Let's see. 1, 2, 3, 4, 5. Are there 5 A's? Yeah, thank you. Everyone's agreeing that it's 5. 5 A's. How many D's? There was 1 D. The D just jumped out at me and it was just sitting there. Yes. How many M's? 1, 2. I'm looking down because I have a tablet down here, but 1, 2, 3 M's. Okay. How many O's? How many O's? How many O's? O's look round. They're easy for me to see. There's 2 of them. How many R's? I see 2, 3. I see 3 R's. Does the crowd agree? 3 R's, yes. And how many Z's? Well, there's only 1 Z. Now, whenever I do a question like this, I'm always afraid that I counted wrong. Do you know a good way to double check? There's a good way, if you do something like this, to make sure you didn't miss any. One way, the way I often do this, is I count up everything. Yeah, so let's add up all of this. How much is here? 5 plus 1 plus 3 plus 2 plus 3 plus 1. What is that? If I was going to add those together, I see 2's and 3's. I like that because 2 plus 3 is how much? 2 plus 3 is 5. So then I can take that 5 and this 5. Come on, hands. There. That's 5. It's so hard for me to point backwards. That's 10. I'm pointing at 10 right now. 10. So that's 10. And what's left is 5 left. So that's the 15. That's a 15. So all this is 15. Okay. Are there 15 letters in this big long thing? Now it's more counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, something's wrong. 4, 8, 9. 9 plus 6 is 15. Yes, there are 15. Okay, yes. And as you can see, this is how I make sure I didn't make a mistake. All right, then the next thing I need to do is I need to know what's the chance that I actually will be picking exactly one of the A, exactly one of the M, exactly one of the O, exactly one of the R. The interesting thing here is that it says rearranged. So indeed, exactly, there are 4 factorial ways to rearrange them. So first of all, there are 4 factorial, which is equal to 4 times 3 times 2 times 1. Rearrangements of AMOR. Okay, so in that case, then that means I could just, since actually the probabilities are going to be the same for each one, I can actually, well, you'll see in a moment, we'll see that come through. But what I'll do is I'll just say, well, what's the chance of getting AMOR? Probability of A and then M, and then O, and then R. In that order is, well, the chance that you get the A first, you're choosing at random without replacement. Okay, so that means there's a 5 out of 15 chance. We figured out there are 15 things altogether. 5 out of 15 chance of getting the A. And then after that, I've got to get the M. There are 3 M's, so there's 3 out of, but it's without replacement, so there are only 14 things left, right? Because one of them's already gone. You took out the 15. There were 15, so you took one away. And then there's an O, there's 2 of them there, okay? Divided by 13 left. And R, there's 3 choices, divided by 12 left. All right, that's the probability of AMOR. I also want to emphasize, I made a comment earlier that it's going to be the same no matter what order I put. For example, the probability of I know, let's have some more fun. AMOR, amor, I think that means love in Spanish, maybe, I'm not sure. But here, there's another word I can make. More. More is how you spell the word more. Just kidding. No, it's not. But anyway, more. How do you get more? So more would be the M. How many M's are there? There are 3 M's divided by 15 choices for the first one. And I'm just doing this to show you that you get the same thing. Okay, so the O, there's 2 choices for the O's divided by 14 things left. Then there's 5 choices for the A divided by 13 things left. And then there's 3 choices for the R divided by 12 things left. And the important thing is when you look at this, you see that the 4 numbers on top are the same and the 4 numbers on the bottom are the same. So that's why the answer is actually just this thing times 24. 4, 3, 2, 1 is 24. All right, so now let's put everything together. If I want to put everything together, I'll just take this. Well, I can take any one of these rows times 4 times 3 times 2 times 1. Because there's 4 times 3 times 2 times 1 of them. I'll write this way, 4 times 3 times 2. I won't write the times 1. And let's just use the second row for fun. 3 over 15 times 2 over 14 times 5 over 13 times 3 over 12. Time to do big canceling. So the 3 and the 12, let's just take this into 1/4. Okay, let's cancel the 4. 4 is gone. What else can I do? Well, the 2 over 14 feels like canceling to the 7 down here. 3 over 15, I feel like canceling down to a 5. Okay. Oh, 5 cancels. Canceling is fun. I don't know about you, but I've always enjoyed canceling. All right, so what else is left? Wow, the top is disappearing. So let's clean up. What do I have now? I have 3 times 2 on top, which is 6. And on the bottom, I just have 7 and 13. 7 times 13 is 91, which is a number that looks prime but isn't. Is that right? Let's find out. So I think the answer is 6 over 91. Let's see if this is right. Yay!
Awesome. And in case anyone else was curious about what the dessert looks like, I, of course, had to go Google it, and here it is. It looks very delicious. I'd love to try it. But on to our next question. Okay. I haven't read the question yet, but I see another weird geodiagram, so let's go ahead and do this. 2 parallel planes, a distance of 8 meters apart, intersect a sphere. Each of the circles where the planes intersects the sphere has an area of 128 pi meters squared. What is the surface area of the sphere? Express your answer in terms of pi and meters squared. And as I've already said, I have never seen this diagram before in my life. I have a sphere, which I don't see often, and then two planes, which I again don't see often. So instead of trying to work with a sphere and two planes, let's try to somehow turn this into a diagram that I'm more familiar with. One that like I know how to do a bunch of tricks with and a bunch of areas. And in this case, yeah, in areas. Well, I don't know much about spheres, but I know a lot about circles, which are kind of like the 2D version of spheres. And I don't know much about planes, but I know a bunch about lines, which are again like the 2D version of a plane. So what if I just took like a small paper thin version of this diagram, just at like almost like a cross section of it? Let's draw this out. Okay, so let's say instead of working with a sphere, I am now working with a circle because I've just like cut this diagram in half and I'm looking at the inside of it. Well, I have a circle and my two planes now become a line. And we can kind of logic this out, but the distance between these two lines and the center should be roughly equal because if I just imagine having like a plane going through my circle, the closer I get to the center of my sphere, that's where my biggest area is going to be. But as I rise up and I get to that very, very top of my sphere, then my area of that cross section of the circle is just going to be nothing. So we can kind of maybe reason out that these two lines should be like equally spaced apart from the center of the circle. Yes. But now we unfortunately have to find actual numbers to this pretty diagram. So we have to jump back to our complicated looking diagram. But it's okay because one of the numbers is very easy to find. The number that's very easy to find is the number that's written out for us, luckily. There's 8 meters. We know that the distance between the planes are 8 meters, which means that the distance between these lines are also 8 meters. And what's really nice is because the distance between the line and the center is the same, we know that this distance here is 4 meters. Okay, and now let's see what other information we can get from our diagram. Well, we know that the planes that intersect the sphere has an area of 128 meters, pi squared. So in particular, let's just focus on this one circle. We know that it has an area of 128 pi meters squared. So what do we know about it? Well, maybe we can figure out the radius from there. We know that the area, pi r squared, is going to be equal to 128 pi. We can cancel out the pi's, and what we end up getting is r squared is equal to 128. And we can further simplify this, so r is equal to square root of 128. But now let's map this square root 128, or this radius of the circle, back onto our diagram. What does that length actually mean in our nicer 2D diagram? Well, the radius of the circle is like half the radius of the diameter of that circle. And our diameter of that circle is just a line. So our radius is just going to be this spot right here, where I start here and I end here. Okay, so that's all the numbers I have. So that's probably all the information I can get from this diagram to this diagram. So now let's actually try to solve the question. The question asks for the surface area of the sphere. Well, I know that the surface area of a sphere is 4 pi r squared. So it'd be really useful for me to find what r squared is. Well, luckily for us, the radius of that sphere is just going to be the same as the radius of this circle. And look at that. We have another right triangle that again tells us the radius of a circle. Okay, in this case, I'm just going to call it r. I'll call it m in this time so we don't get confused with this r. But we know that m squared plus is equal to square root of 128 squared plus 4 squared. And now looking at the square root of 128, we could have just left it out here and just directly gotten it from that, but it's okay. I think it's a little bit more clear to have the square root of 128. Okay, So m squared is equal to 128 plus 16. So m squared is equal to 144. And if you guys know this well, we can find that m is equal to plus or minus 12. But luckily for us, again, we don't have to do the square root because what we're looking for is 4 times pi times that radius squared. And so even though we can find the radius, what we're really actually looking for is the radius squared. And look, that's the radius squared. So our answer is going to be 4 times pi times 144, which is 576 pi. Yes, and I just want to touch on something Andrew said really quickly, and that is we can't have negative side waves. And in particular, what I mean is when I got to this m squared is equal to 144, I actually have two solutions for m. I have m is equal to 12, but I also have m is equal to negative 12 because negative 12 squared is also 144. But let's just take a step back and think about what m represents. M represents a length. So what would a circle of radius negative 12 even look like? Maybe it would look like a donut, I don't know. But because it doesn't make sense, m is 12. So yeah, so sometimes don't get too lost in the variables and think about what they mean. Yes.
Awesome.
Okay.
And yeah, I don't know if you guys can see it, but we did get the answer right. So great job. And we are now on to target number 8. So this question says, each workday when Kate arrives at the office, she does one of the following. Either Kate says good morning to her coworkers, or Kate says nothing to her coworkers. On Monday, Kate says good morning to her coworkers. If on each subsequent day, there's a 75% chance that she will repeat her previous day's behavior, what is the probability that on Friday, Kate says good morning to her coworkers? Express your answer as a common fraction. Ooh, I really like this problem. So what this means is if on Monday, so we're going to do a check mark for says good morning and an X for doesn't. Okay, so if we did say good morning one day, then the next day, it's going to be a 75% chance or 3/4 of saying it again and 1/4 of not saying it the next day. Okay, and then that means on the third day, we'll have a 3/4 chance. If we did say it the second day, there's another 3/4 chance of saying it and 1/4 of not saying it. And then for if we have our X here, then we have a 1/4 chance of saying it and 3/4 of not saying it. But we're going to Friday, right? Although we do have a calculator, we could bash it out. Let's try and think of another way that we could work through this problem. So let's see. What really matters, it doesn't matter what we say in the middle, it just matters how we end up. So all of our different possibilities here, they have to start in a check mark because that's what we're given, and they have to end in a check mark because we're told that they end in a check mark. We're trying to find the probability that it ends all good. People are saying we should draw a tree. We could definitely do that, but that'd be really, really big. Okay, so now that we have these here, we've got 3 blanks that we need to fill in. And any single one of these blanks can be an X or a check. So why don't we figure out the number of ways that have switches and the number of ways that don't have switches. So let's just write out the 8 different possibilities that can go in the middle here. So we can either have checks for 3 days, 2 checks and an X, a check, an X, and a check, an X, and an X, or we can have all of these but an X in the front. So that's X, check, check, X, check, X, X, check, and 3 different X's. So of our possibilities here, we want to see how many switches there are in each. So in our first case, we're never switching. We're going to stay in a constant check the entire time. So that's no switches. Right here, well, we're going to not switch here, not switch here. We're going to switch at the end, but it's not one switch like it might seem because we have to end in a check again. So there's actually going to be 2 switches in this situation. Same thing here. We're going from a check to an X to a check. That's 2 switches. Even though there's 2 X's now, there's still 2 switches. Once again, 2 more switches here. This time, we have a lot more. We're going from a check to an X. That's 1 check. That's 1 switch. The X to the check. That's our second switch. A check to an X. That's a third switch. And an X to a check. That's 4 switches. Okay, and let's go here. We've got 2 more X's, but because the way that they're set up, it's only going to be 2 switches. And lastly here, even though they're all X's, we're going to have 2 more switches. So what does this tell us? We know that every time we switch, there's a 3/4 chance of switching. So if we wanted to figure out the number of totals, or sorry, there's a 1/4 chance of switching, not 3/4. So if we want to figure out how many, like what the probability of going through a situation with no switches, well, that means that for the 4 days, we're going to follow the 3/4. We have 2 switches. That means on 2 of the days, there's a 3/4 chance of making it. So we're going to raise this to the 4th power from our first one. For our second case here, there's a 3/4 chance of making the switch, of not making the switch, and 1/4 chance of making the switch. But because each of these have to happen twice, we're going to raise them the 2nd power. And this is the same thing for all of our 2 switches here. So because there's 1, 2, there's 6 of them, we're going to multiply this by 6. And lastly, the only case we have left is 4 different switches. So if we have 4 switches, then what that means is we're going to have to switch every single time. And the probability of doing that is 1/4 to the 4th power. Now, what we could do is just add all of these up and get our probability. So that's where it's really good that we have a calculator. So let's go ahead and do that. That's 3/4 to the 4th power plus 6 times 3/4 squared times 1/4 squared. And then lastly, we're going to add 1/4 to the 4th power. Oops. It's really hard to put all this in the calculator, like Po-Shen Loh was saying. And when we do all of that, that'll give us 17/32. So that looks pretty good to me. What do you guys think?
Yes, that is actually the correct answer. This is really interesting. So like we have different ways of doing the same problem and getting the same answer, so it had to be right. So let's see. Yes, it is. Actually, your way is pretty clever. In fact, your way is possibly faster than what I was doing. But it's really interesting that you were just like, let's group together the things which will have the same arithmetic anyway. I thought I would share another way, just because this is related to something I was teaching in my class at Carnegie Mellon University. This is actually related to matrix multiplication, but that's too complicated for most middle school students. So maybe I'll just say, here's another way of looking at the same thing, and then you'll notice an interesting pattern that comes out. So the way to read my chart is I was also inspired by the check mark and the X, but I put some eyes on top. So this is the says good morning. This is the doesn't say anything. Okay. And so on Monday, what I'm writing here is I'm writing the probability that the person, what's the person's name? Kate. What's the probability that on Monday, Kate says good morning? Well, it's 1 because Kate says good morning on Monday. What's the probability Kate says nothing? Well, it's 0 because Kate says good morning on Monday. Now let's look at Tuesday. The way I go from Monday to Tuesday is I say, so if there was a definite chance that Kate would say good morning, well, I guess the question is, how do I get to saying good morning on Tuesday? The way to get to saying good morning on Tuesday is either you come from the saying good morning on Monday, or you come from the not saying anything on Monday. These are different color arrows. So what I mean is the yellow arrow is that if Kate already said good morning on Monday, then the chance that Kate says good morning again on Tuesday is times 3/4 of that. So because there's a 1 probability that Kate said good morning on Monday, there's a 3/4 chance that Kate says good morning on Tuesday coming from that 1. There's another way to get here. It's to go from this one, but actually there's nothing here because there's no chance. Kate didn't say good morning. So even though originally you might have noticed I didn't even have the pink arrow. Pink means it's going from something they didn't do the previous day to something that they did do the next day. So now I know that this top number is 3/4. On Tuesday, Kate has a 3/4 chance of saying good morning. Well, can anyone tell me if that's 3/4, how did I know this is 1/4? One way is to do a whole lot of arithmetic, but there's a much easier way. If on the Tuesday there's a 3/4 chance Kate says good morning, then indeed they have to add to 1. So whatever I have here, I do 1 minus to put there. Okay, now the magic starts to happen. Not magic, the mess starts to happen on the next one. So if I want to know what's the chance Kate says good morning on Wednesday, either it's because Kate said good morning on Tuesday and then said good morning again, or it's because Kate didn't say anything on Tuesday and now says good morning. So where does this fancy expression come from? Well, the 3/4 squared is just, there was a 3/4 chance that Kate said good morning on Tuesday, and then times 3/4 of doing it again. The first term is from starting there and then going over here. I see a lot of people are putting it this way, of like they're looking at the way it works as well. If I, or I could get there by starting from the didn't say good morning, and then suddenly says good morning. This is what Jesse was doing at the times 1/4, right? So like there's a chance that I start here, Kate starts here, and then does the opposite. So that would be plus 1/4 times the 1/4. That's this 1/4 squared. Okay, so then now I have to just add this. So I added this in my head. I said this is 9/16 plus 1/16. That was 10/16. Simplifies to 5/8. And then if that's 5/8 that Kate says good morning on Wednesday, how do you get this number? Well, we don't have to do a lot more like fancy calculation. It's just that the chance of Kate saying nothing plus the chance of Kate saying good morning add to 1. So, okay, that's how much this is. Now let's keep going. The thing is, this keeps going. So if I want to know what happens on Thursday, for Kate to say good morning on Thursday, either it was that Kate said good morning on Wednesday and then says good morning again, or Kate didn't say anything on Wednesday and now changes her mind. So now you can see the way this always flows. I always would take, if I'm going across with the yellow, I'll take the chance that Kate said good morning times 3/4 to say good morning again, plus going the other way. So Kate didn't say anything. Why is Thursday the letter R? Because T is the same as the first letter of Tuesday. So I don't know, I grew up always writing R for Thursday. But so then I take this thing times 1/4, and then that gives you this expression. You add them up, and the way I added them was 5 times 3 plus 3 times 1. To me, that's 6 times 3. I always like to factor if I can. So 5 times 3 plus 3 times 1, that was 6 times 3. And 6 times 3 divided by a bunch of power of 2, I just thought that would be 18 divided by 32, cancels, becomes 9/16. Okay, and then if that's 9/16, if this is 9/16, this is 1 minus, which is 7/16. At this point, I said, usually with these questions, if it's going to follow this nice, it's called a recursive pattern. If it's going to follow a recursive pattern, then it usually has a pattern in the answer. Can anyone see a nice pattern about the answers? Because actually, it is true, by the way. If you always make the next thing by following the same kind of formula of the previous thing, then it has some kind of pattern, right? And I see, Nathan, you're almost right. N plus 1 over 2n. So it's close, right? It's basically like just over half. It's just over half, except that the bottom just keeps being a bigger and bigger power of 2, and the top is just a little bit more than half of it. It's more by 1. So actually what ends up happening is that we did it, like we just did it again. If you do the calculation again, you see 17/32. But the fun fact is, if you saw this pattern and then somebody asked you what happened, like in a month, you would be able to just be like, yeah, well, it follows the pattern. So you just take a big power of 2 and take like half of it minus 1. In high school, you learn about matrices. There's something here where it's actually about, it's a matrix. So I mean, because we got high school students here. We also might have some high school students watching. Actually, the way you get the next one, the way you get like from one to the next is you actually multiply like some matrix. And the matrix actually is something like 3/4, 1/4, 1/4, 3/4 times the previous good morning, say nothing, is equal to the next good morning, say nothing. So actually that's That's exactly what's going on. To get to the next one, what I did is I took 3/4 times the smiley plus 1/4 times the say nothing. But anyway, this is just if there are some high school students watching this. This is what's here. And I'll say one more fun fact about this. If you look at what happens if you were to do this for like an entire year, then the two fractions are very, very close to half. And that actually makes sense, because if you did this for an entire year, then you just have forgotten where you started. Like, what's the relevance of where you started? By the end of the year, it's like, okay, are you saying good morning? Are you ignoring me? I don't know. It's 50-50 at this point, because the whole thing of like, are you off by one or not? That one day doesn't matter after a year. Okay, anyway, I just thought this was a really cute question, so I wanted to say a few things.
Yeah, it was definitely very, very cute. And my favorite part about this question was I didn't realize it was going to go to 1/2 as the answer, like as we got farther and further. But in hindsight, obviously, it does make sense that after a while, what I said on that one Monday a long, long time ago is insignificant. But moving on to our next question. So we're now on the team round questions, which are problems intended for you to solve with a team. So these might be a little bit more challenging, but we shall see. In dynastic China, a K was a unit of time, measuring 1/4 of an hour. How many K are in one non-leap year? Okay, so this is very interesting because we are again doing time conversions, just like my first previous problem on the time round, which is very interesting. But yeah, it's asking for how many K are in one non-leap year. So let's just start with a year, because we're trying to find how many Ks are in one of them. So let's see how we can turn this year into a K. Well, looking with a bit of foresight, we know that a K is 1/4 of an hour. So we know the relationship between an hour and a K. So it would be very helpful to have this year be expressed in hour. So we know that 1 year is going to be equal to 365 days because we are dealing with a non-leap year. And we know that every day can be expressed as 24 hours. And now I'm feeling really happy because we're in hours, and I definitely do know the relationship between Ks and hours. I know that 1 K is equal to 1/4 of an hour. So 1/4 of an hour is going to be equal to 1 K. So because I have a fraction here, in the denominator, what I can actually end up doing is I can just flip the fraction and move it to the top. So I get 365 times 24 times 4, and we can solve that from there. But the really nice thing about this question is, well, I see that this 365 ends with a 5. And, well, this 4 times this 5 is going to end up giving me like some number that ends up with a 0. And I really like multiplying numbers that end with 0 because, well, I don't really have to worry about the 0 bit. So let's go ahead and do 365 times 4 first. Well, 365 times 2, that's going to be 730. And 730 times 2, that's going to be 1460. And just like I expected, there's a 0 there, which makes me very happy because instead of multiplying 1460 by 24, I can now just multiply 146 by 24. And now there are a few tricks here, but I think I'm just going to go ahead and multiply that out because I don't think like doing anything is going to make it a lot easier. But as I said before, we can kind of ignore the 0 and just do 4 times 6, which is equal to 24. And then 4 times 4, 16, 8. And then carry the 1 there, and then 4 times 1, so that's 584. And then we get a 0. 2 times 6 is 12. 2 times 4 plus 1 is equal to 9. And then 2 times 1 is equal to 2. And adding that back up, I get 4, 0, 5, 3. And we can't forget about the 0 that we forgot at the beginning, or purposely forgot at the beginning. So we'll add that back in there. And so we get that 1K is equal to 35,040. Oh, I'm sorry. 1 year is equal to 35,040 K. And hopefully that is our answer. Yes.
Awesome. And with that, we move on to question 2. This question says, the students at Somerset School are going on a field trip. there will be 270 students and 24 teachers on the trip. Each bus can carry 42 passengers. How many buses are we going to need? So the most important thing that I see here is that there's no difference between how much space a student and a teacher takes on the bus. So what we got to do now is just see how many people are there total. So the total number of people, or P, is just going to be the number of students plus the number of plus the number of teachers. So that gives us a total of 294 people that we need to fit into buses. Well, what we got to do then is just divide by 42 to see how many buses it'll take. So 294 divided by 42. I believe we are allowed to have a calculator on this one. So we can just go ahead and plug that in. Although if you want to do it in your head, you totally can. But this will give us exactly 7, which is really nice for us because something that's really important to notice is that if, say, they had given us 295 people and we still had to fit that into buses of 42, then it would give us, well, it would be slightly more than 7. We would get, if my calculator will work, that's okay. We'll get 7 point something, right? It'll be just a little bit over 7 buses. And if that happens, we can't round down to the nearest integer like we normally would. We have to round up because we have to make sure that everyone makes it to the destination. So you got to round up anytime that it wants you to fit people into a bus, and you have to say the fewest number of buses you can have. That's really the trick with this problem. But luckily for us, it divided perfectly. So our answer is going to be 7, and we can go ahead and check that. Answer 7 buses, so we got it.
Yes, this is good. And somebody, Sophia asked, does the bus driver count? Well, the good news is it said this is how many passengers it can carry. And usually if it says passengers, that's not counting the driver. Fun fact, when you go on a field trip, you got to make sure that on the buses, you don't just put all the teachers in the bus. But in this particular problem, it was okay. We just said teachers, students, you're all passengers, P. But I'm pretty sure that nobody sends their students on field trips where they put all the teachers in one bus, and the rest of the ones are parties. Okay, right. So with that, we're getting close towards the end of time, but there are some pretty interesting questions in this team round. Which ones should we do? Well, maybe let's not just go straight in order. So I don't know, what should I do? I'm just gonna myself bounce deep into the questions. Okay, so I'm just gonna jump all the way to question like 7. Let's see what this is. I have no idea, by the way. I've never done the questions before. So let's see. So let's maybe do 3 more questions, even though we're almost out of time. And between the 3 of us, we'll sort of figure out how to help each other. And of course, maybe one of us will choose question 10 at the end. But I'll jump to 7. I chose the 7 so that I'm not forcing the hand of my co-stars. Because if I started with 8, then we don't have much choice. Okay. Whoa, what is this? Okay, how many different non-congruent right triangles with integer side lengths have a perimeter less than 75? These don't look that easy. Okay, so now I have to deal with integer side lengths. So I need to use the fact that there's a bunch of very common triangles that come. These are like 3, 4, 5. I'm not going to draw triangles because that will take me too long. Okay, so now there's like a whole lot of these Pythagorean triples. And I guess this question is here to go and make sure you know all of your small Pythagorean triples. There's a 3, 4, 5. There's a 5, 12, 13. By the way, if you have a 3, 4, 5, you can also double each of the lengths. So there's also a, I'll write the times 2 version. This is a 6, 8, 10, right? So if you just double the 3, double 4, double 5, that's also a right triangle. Okay, 5, 12, 13. What else is there? Does anyone know? There's also 5, there's also 7, 24, 25. Okay, so far the perimeter is okay. There's one of these hiding in there. There's always this 8, 15, and 17. Okay, and then there's a 9, 40, 41. How do I know this? I don't know. It's probably because I just did math counts before. When you do math counts and math competitions, you kind of run into these a lot. Okay, and what else is there? So by the way, these things that are going like 9, 40, 41, these are getting kind of long and pointy, which means it's not very good for this perimeter less than 75. And this is a tricky question because if you go here, you're like, well, that's it, right? I mean, anything else I go is going to be even more pointy. But actually, there's more. there's actually this really tricky one hiding inside there, which Nathan Liu is telling us. Don't forget 20, 21, 29. This seems like a very easy one to forget, because that one actually adds up to less than 75. Probably this question was very hard because probably people didn't notice that one. Because for a lot of people, they probably thought, look, this is already too much and there won't be anything else. In general, there are actually formulas to go and produce all of these, but that's actually sort of beyond the scope of this. So, all right, beyond the scope of our time in this live stream. So, okay, now I just have to know how many of them have the perimeter less than 75. So there's the 3, 4, 5. What's the perimeter of 3, 4, 5? Well, it's some of them. 3 plus 4 plus 5, that's 4 times 3, which is 12. Okay, so that's 12. All right, so if that's 12, I can do 12 up to 12 times 6. So I can do times 2, all the way to times 6, because 12 times 6 is 72. 5, 12, 13, that adds up to 30 already. So there's also a times 2. 7, 24, 25, that's already looks pretty big. So I can't even have a times 2 version. 8, 15, 17, what is that? 23 plus 17. Yeah, so 23 plus 17 is 40. Oh, but that's it. 40 means that I can't have another one. Okay, so that's it. 9, 40, and 41, that's too big. That one doesn't even count. And 20, 21, 29 does count. So if I look at this, it looks like the answer is there's 6 of these. The answer is 6 of those plus 2 of the yellow ones plus 1 of the blue ones plus 1 of the pink ones plus 1 of the green ones. Yikes, is this right? I don't know. Whew, it is right. And thanks to the chat for 2021, 29.
Yeah, these questions are so difficult. I'm like definitely very, very surprised. But I guess that's the whole point of working in a team, because everyone is good at different things. Everyone is going to notice different small mistakes, such as a 20, 21, 29 triangle. And so, yeah, okay. Let's take a look at the next few problems. This is a geo problem. I kind of want to do another geo problem. Probability problem. I don't want to do that either. Okay. Algebra, or number theory. We can do this. Okay, so how many 2-digit positive integers have exactly 3 positive 1-digit factors? Okay, there is a lot to break down here, but gotta start somewhere. Well, first thing I notice is that 1 is always going to be a factor of every single number, because 1 divides everything. And also, 1 happens to be a 1-digit number too. And so 1 is definitely going to be one of my factors. And from here, I guess we can do a little bit of casework. Let's just say my next number happens to be 2. Well, if my next number happens to be 2, then I guess my third factor could be 3, in which case I would get have a number with a multiple of 6. But this is an issue because 6 itself is a 1-digit factor. And so if my number was a multiple of 6, well then 6 would also be a factor and I would have more than 3. Okay, so 6 obviously does not work. So let's move on to our next factor of 4. So the thing with 4 is that 4 also happens to have a 2 in it. And so that means my number can be basically any number that is a multiple of 4. But the issue is, okay, I can have 4 as my number, which is unfortunately not a 2-digit number. I can have 8, which is unfortunately not a 2-digit number. But anything from 8 and beyond is going to have a factor of 8 in it. And so unfortunately 4 doesn't work either. So let's take a look at our next number. Hold on, did I make a mistake?
I'm gonna jump in because I'm curious. I don't know how to do this either. I'm like thinking at the same time. But I think you can do like 4 times a prime, like 17.
Oh, okay. Yeah, I think you're right.
But I don't know the answer yet. I'm still thinking at the same time as you at the same speed. So keep going. Because I'm like, I think you can do 4 times a prime, but there's like, how do you do that?
Okay. Yeah. Okay, so we can definitely do 4. But okay, I think I want to re-change my method of doing this, y'all. Like, I think this is not it. Instead of looking at the numbers 1 through 10, let's look at the problem to 10. Because there's just too many numbers, and I thought about this, and I was like, shoot, I'm going to have to go through 100 numbers, and we're going to be here until 3 a.m. in the morning, which unfortunately is a little past my bedtime. So let's look at our prime numbers from 1 to 10. So we have 2, 3, 5, 7. And yeah, okay. Well, this helps us a little bit because we just narrowed it down from 10 numbers to 4 numbers. And let's first start with the case where my 2 prime factors are co-prime. What I mean by that is like, for example, maybe I have something like 1, 2, 4, and like Professor Loh said, something like 4 times 17, which has factors 1, 2, and 4, and um 17 and so on. But like 2 and 4 aren't exactly co-prime. So let's say my positive factors are less than 10. And that are less than 10 are also co-prime. Okay. So that helps us because we know they are either 2, 3, 2, 5, 2, 7, 3, 5, 3, 7, and 5, 7. Now, we already eliminate 2 and 3 because we know that 2 and 3 has that 6, and we know that 6 is also a one-digit number, which is really bad for us. Well, 2 and 5, what's that? 2 times 5 is 10. So 10 actually ends up working out for us. And I also wonder, does a number like 50 work out for us too? Well, what is 50? 50 has prime factors of 1, 2, 5, and 10. So something like 50 also works out for us. So it seems like for these numbers, even though I've chosen my 2 factors, I can like multiply them by factors of themselves. And I can also multiply them by factors that are not positive integers from 1 to 9. So for example, I can also multiply this number by 13, but unfortunately 10 times 13 is too big, in which case, so that's just not a possibility. And by the way, this question is very tricky, so if any of you guys would like to help me out,
Yeah,
very appreciated.
I'm doing it at the same time as you at the same speed, sort of. And I'm just like checking what you're saying. Seems to make sense.
Okay.
So I like how you're splitting into the cases. That sounds reasonable. And so the 2 and the 5. So if it's got 2 and 5, I think 10 and 50 are the only ones you can do. Because like 30 is bad because 30 would pick up a 3. And you're in the case where there's no 3. Right?
Yes.
You're saying like it's 1, 2, and 5 are the only ones. So I was actually just going through, I was like, what can I do? And I can't do 20. I cannot do 20 because 20 would pick up a 4. So I saw you were
Exactly.
multiplying like the 10 times some prime number, and you don't want to multiply by 7 because then a 7 would appear. So I think I'm just like making a list, and I'm like the 2, 5, I like it, 10 and 50. So
Okay.
maybe I'll take the next one, and then let's just see what happens. So the next one, maybe you guys can check me because that would be useful. So if it's a 2 and a 7, following your same logic, you can do the 14, right? Because 14 is going to be okay. 14 will only have the one-digit factors 1, 2, and 7. And then after that, I cannot do 28 because if I jump to 28, then that's going to pick up a 4. And then I'm not good because I have too many one-digit factors. I also can't multiply by 3. I could multiply by 7. I think what you've noticed here is that you can multiply by the same one as long as the square of that one is not a one-digit number. Like you could multiply by the 5 here because this has 25 as a factor, but 25 is not counting against you. I could not multiply 10 by 4 because the 4 would count against me. But now coming over to here, 14 I can multiply by 7, and multiplying by 7 is 98. So I think there's only 2 in that case.
I think so too.
You're writing down a whole bunch of stuff. So do you have more stuff now?
Oh yeah. I'm always just trying to think along with you and trying to think a few more steps. So yeah. So jumping back to 3 and 5, Professor Lowe also has this written exactly on his screen. We get 3 times 5 is 15, and we notice that 3 squared is 9. So if we were to multiply by a factor of 3, this would cause issues because then we'd have a factor of 9. And so the only possibilities are 15 and 75. And then we can jump to 3 and 7, and we get 21. And we try multiplying by 7, doesn't work out. We do the same thing with 5 and 7. We try multiplying by 5 and 7, doesn't work out. So now we've covered the cases where there are at least 2 co-prime one-digit factors. So let's think about the case where the 2 factors are not co-prime. For example, just looking at 27, right? 27 has factors 1, 3, 9, and 27. And so yeah, it fits our criteria of having 3 one-digit positive factors, 1, 3, and 9. But it doesn't exactly fit into one of our categories. So Professor Loh, what can it
Yeah.
differentiate?
So I'm looking at that, right? So that's the one that I was thinking about earlier when we started doing this. I'm going to do it with the 2 and 4 first because I think it's inspired by the same as 3 and 9. This could be wrong, by the way. I'm just like thinking as we go. But if I wanted to have 1, 2, and 4, that's where I was like the 4 times 17 was okay. 4 times a big prime number is okay, where big means bigger than 7. Like somehow the prime numbers down here are dangerous. If I took 4 times 7, I'd get 28, and then a 7 would be another factor. So it looks to me like what I can do here is take 4 times any collection of primes, or like powers of primes. So it's like times primes, which are at least 11, times maybe more of them. Right? I'm gonna say I think that's how I can do it. Although actually, now that I look at this, if I multiply 2 primes, which are at least 11, and multiply by 4, I'm dead, because that's like bigger than 100. So in that case, now it looks like this is just 4 times primes, which are at least 100, at least 11. What? I need to know how many there are. Well, but actually I don't have to go that far because it's times 4 anyway. So if I was to make a list, well, there's 44 is one of them. 4 times 13, whatever that is, 4 times 17, 4 times 19, right? Because each of these, if I factorize them, they're only going to have 1, 2, 4 in the one-digit prime factors, one-digit factors, and then like other big stuff. And then it's 4 times 23, and I think that's it, because 4 times anything bigger, it blows up. So here I've got a bunch. And then using the same logic, that's what Michelle, you wrote with the 3 and 9. The 3 and 9, that would be 9 times any primes at least 11. But now I'm seeing I'm wrong. The reason I'm seeing I'm wrong is because 27 was also okay. Oh, in that case, you can also have 9 times 3. So I'm really glad you wrote 27, because I would have forgotten 27. Because the thing about the 27, okay, the thing about the 2, 4, I couldn't do 2, 4. I couldn't get like an 8. Because if I got an 8, then it would have a 2, 4, and an 8. But over here, I can actually have a 27 because 27 is not one digit. So it's actually 9 times primes at least 11, or 27. I would have actually missed that if you hadn't written that down. Okay, let's try this. 9 times primes at least 11. There's only one of them. 99 or 27. Okay, so I'm coming up with these 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't know. Is it?
Okay, hold on. Let me check.
Oh no, we're off by 1. Which one did we miss? Jesse, which one are we missing?
Hey
I
guys,
realized
you
I
gotta
was
help me
off
out
by
here.
1.
Which one are we missing?
I did it a really similar way. So I listed out all the pairs also by finding the ones that don't work. And I actually forgot to exclude 2 and 3. So I was over by 1.
Oh, okay.
Okay, but where are they? So I mean, we should be able to find all of them, right? They should all be here somewhere.
Okay, hold on. I'm getting 16 and 63. 16, I don't like works because you can have 1, 2, 4, 8. 63, you have 3, 7, 9.
Ooh, you're right. That should be over here.
Wait, but we have 3, 7, and 9, so it's 4.
No, that's no good. That's no good. What are we doing? No. No. 63 doesn't work. Okay.
1, 2, 3, 4, 5, 6, 7,
Which
8,
missing? Where did we miss it?
I bet you there's a better way to do this question too. That's why I really wanted to bring it up. I was hoping that we could find some clean solution.
To be honest, I think your way is pretty good. I was actually doing something pretty good. Oh, somebody's saying check the chat. Okay, you gave us all the numbers. So we're all working together now. 14? Where's 14 coming from? Oh, it's
Okay.
there. We have that. Which one is
45,
not there?
45 has 1, 3, 5, and 9. Y'all, hurry up and comment clutch here. Please help us. Okay, Andrew, 14. We have 1, 2, and 7. We have 14, so I don't think that's necessarily
Andrew Lin has this big list of numbers. Is there anything in his list that's not in our list?
About the 4 and the 9. Well, 4 and 9 work, but they have to be two-digit positive integers. So even though it does satisfy one of our criteria, it's lacking in another one.
Oh, 81. Somebody listed 81. Oh my gosh.
Oh,
81 is like your 27. So that's the one that, okay. Because I actually, to me, you see, I have this weird or 27. And the reason there was an or 27 is because Michelle's screen had 27. I was like, it actually works. But all the rest of these, like they follow the pattern. It's like times these primes bigger than bigger, at least 11. And then this thing here was just because, oh, you found one. But I guess the theory of what you found is this thing is special because it's just more power of 3. Right? Like that's why that works. There's no other prime factor. And it turns out there's one more power of 3 that you can put up. Or 81.
Yes.
That's the
You
answer.
see, I had 81. I was missing 99 and I didn't notice it.
Wow. Okay. I have to say this is a teamwork question. Thank you, crowd, for being part of the team. But I also want to say, Michelle, you were looking for a better way to do it. I actually think your way is pretty good. Your way is pretty good. I think it's very clever. I was going to do something much worse. And as you started doing this, I was like, it actually is quite reasonable. We forgot 92?
92?
1, 2, 4. I don't think so. That's 4 times 23. We got it. We just didn't expand it.
Okay,
So,
okay. We're
yes.
good. We're good.
Round of applause for the crowd. Okay.
Yes.
I think here's what I'd like to do. Since we all kind of collaborated on this one and we're way over time, let's call it a night for now, just because let's call it a night for the math part, and just say, it's been lots of fun working with all of you. I want to say, if you like these, we do encourage you, make sure you participate in Math Counts next year. It's a real pleasure to collaborate with Math Counts because, well, Math Counts for many of us is how we got introduced to interesting math problems. If you like what you saw, by the way, we have live streams running on this channel all the time. In fact, usually the live streams are wonderful and very exciting because we are trying to figure them out as we go. And if you just continue watching our channel, you'll see us. Actually, we'll be here this week doing a couple of them. With that, I want to thank my co-hosts, Jessie and Michelle.
Thank you. It was awesome working with you guys.
It was so fun.
Great. And have everyone. Bye-bye.
Bye.
Bye.
Bye-bye.
Thank you guys. Oh, I'm still.
Yep, no problem. Bye-bye.
Bye.